This video is for the Avenues Online Global Elective Statistics. It will also show you the review of polynomial functions for the regression unit that we will be doing. First thing we need to do is just review what a polynomial is for yourself. A polynomial is an expression consisting of the sum or differences of algebraic terms. And when we say algebraic terms, we're talking about a monomial, which is just one term, that is of the form a times x to the n, where n can be any number from 0 to a lot. We are generally used to seeing terms of the degree 2, 3, 4, even 5 sometimes, but we will probably only be working with polynomials that have degree, meaning the highest exponent, of maybe 4. So the a in the that is multiplied, that is the coefficient, can also be used as a positive or a negative number. When Desmos creates a regression function, it uses the standard form of a polynomial. We've already seen how the linear model is of the form y equals ax plus b. A line is a polynomial function with degree equal to 1. Another example of a polynomial function is a quadratic function. This has degree 2, and the standard form a cubic function has degree 3 and has standard form and a quartic function has degree 4 and has standard form of Notice that all of the variables a, b, and c represent constants that can be positive or negative, fractions, decimals, any type of real number that you have been using. Each type of function has its own unique type of graph, and that's what we're going to look at next. The graph of a quadratic function is usually called a parabola. You probably have studied this in a prior math course. Just to review, let's look at these constants and how they change the graph. The a, that is the coefficient of the x squared term, usually changes the steepness and direction of the parabola. Positive a means it's going up, and negative a means it's going down. The b doesn't change the shape, but the location of where it is on the graph. And the c determines the vertical shift of the parabola. You will use quadratic regression when you decide that a data set doesn't look linear or when the residuals have a pattern of some type. If you've studied cubic functions before, you are familiar with the graph of a cubic that has at most 3 places where it crosses the x-axis, also known as the roots or the zeros of the function. The a coefficient again changes the steepness of the graph, making it higher or lower, but also changes the direction, whether it is strictly increasing or decreasing. And this strictly increasing or strictly decreasing only happens when the other 3 coefficients are 0, and the function goes through the origin. The b coefficient changes the locations of the maximum and minimum values, both the height and the width. The c coefficient changes the height of the maximum and minimum values, which can also be seen as kind of the curvature. The d, again, changes the vertical shift of the graph. It also changes the y-intercept, or the place where the graph crosses the x-axis. A quartic function is a polynomial that has at most 4 zeros, or roots. Its standard form is just an extension of the cubic one. I can't use the letter E in Desmos because it represents a number in mathematics, so I just put an F there instead. Some of these variable constants don't have a unique effect on the graph, but you can see how some of them do. The A coefficient, again, just changes the steepness, but also the direction. The B, C, and D coefficients have an effect that is similar to those in the cubic function, changing both the x-intercepts and the location of the max and mins. Here is a cubic that has 3 roots, or zeros, and here is one that has 4, depending on where it is. The F constant, which is often an E, still moves the curve only vertically, changing the y-intercepts. In statistical regression, it is often the case that the data doesn't have all of the curves that cubic and quartic polynomials have. We can see a curve, but don't really know how fast it's increasing or decreasing, whether they're max and mins, and it turns. So in this case, we use what's called a power function. This is a function that has only one term, a coefficient, and a variable raised to a power. In this case, in order to fit the data well, the exponent may be any real number, as opposed to in a polynomial, where the exponents are all whole numbers. When the exponent is negative, let me keep them negative, the curve looks like this that we see, and we don't usually look at the left-hand side of the graph because data usually only has positive x values. So we would only be looking at the top right-hand corner. When the exponent is positive, the curve looks similar to a parabola or another polynomial. Finding the power function that fits the data is called power regression.